Yeah, so hello everyone. Thanks for coming in Friday morning. Hope everyone's doing well in homework one. Oh, by the way, can everyone hear me? I just want to check.
Yes.
Oh, thank you, Danish. Yeah, so hope everyone's doing well with homework one. Homework. So please note, homework one's both part one and part two are due February 28th, and uh, for homework one, part one, it's like a hard deadline, so you can't use Slack days for homework one, part one, but you can use Slack days for homework one, part two. And also for this semester's homework one, part two, there's like a larger number of features, so it requires a lot of memory and computation. So try to have try to, if you haven't have like a baseline working, try to have it as soon as possible. And we've also posted the grade cutoffs for homework one, part two, and the baseline architecture on Piazza, so hopefully that would get you off with a good start. So today's recitation is about optimizing neural networks, and let me go ahead and share my screen. Yeah, so there's supposed to be two parts. I think the other I think Shentong is having some connection issues. I think I contacted him like 10 minutes ago, and I think he might be joining later in the recitation. But so for the first part, I'll be talking about optimizers and initialization methods. And the second part, Shentong will be talking more about other strategy that will be useful for optimizing your neural network. So the main contents for today is first we're going to talk about gradient descent, stochastic gradient descent, and mini batch gradient descent. And also we're going to talk about improvements of gradient descent, which includes Newton's method, Armis prop, momentum, Nesterov's accelerated gradient, and atom. And finally, in the last part, we're going to talk about initialization methods and why initialization is important, including Savior and K-mean initialization. So, so right now, the current state is you're trying to solve some task through deep learning, and you have your data, and you have your finalized initial network architecture to train. So now you're trying to train and learn the network parameters. So um, wait, let me. So I guess the problem is how are you going to minimize the loss function with respect to the network parameters? And there's this basic approach, iterative approach of gradient descent, as you guys all know. So we're trying to iteratively improve the network parameters to reach the minimum point according to the loss function. So there's three types of gradient descent methods. First, batch gradient descent is just the same thing as gradient descent. So basically what it does is it goes through all your trained data, and then it takes the mean of the gradient and for all the samples, and then after looking through all the samples, it's going to take one large step towards the minimizing direction of the gradient. And the good thing about it is it's actually mathematically provable, and it's actually guaranteed to converge to a global minimum for convex surfaces. If you took like courses like convex optimization or uh, you would know that it's kind of related to the L smoothness of the loss function surface. So if you have a sufficiently small learning rate, it will reach the global minimum, and also it would reach the local minimum for non-convex surfaces. And also it however, it kind of tends to be slow because you have to look through the entire entire like training data until you take a step forward, and it can't be performed in an online fashion. So that might be like a downside. So in the other hand, stochastic gradients descent is like actually updating your network parameters right away at when you as you see each training instance. So it's faster and you have more frequent updates. But the downside is it has high variance because you're you would be um, updating your parameters according to each like one sample of data, which would be swinging your parameter values too much. But it could be done in an online fashion. But because of that, convergence usually becomes an issue with SGD.
Excuse me.
Um,
Do you think you could possibly zoom in a little bit?
oh yeah, sure. Yeah, is that better?
Yes, thank you.
Okay, yeah. Yeah, so I was talking about SGD. So um SGD usually convergence becomes an issue, and but with an approximate scheduler or of learning rates, you could actually make it to a behavior close to batch gradient descent, and you have opportunities to jump between local minimums and kind of search for explore a more larger subspace of the parameter space. So mini batch gradient descent, what we usually do, and what we're actually doing for homework one part two. If you have started it or implemented the data set, you would see that you actually get a mini batch of the training sample data, and then you use that entire batch to compute the gradient, and then update your parameters according to that mini batch result. So this kind of gives you the stability of like converging of your parameters, because you have a mini batch and you have some kind of average direction of where to step to by having that mini batch. And it can also be as fast as SGD, because um, after each mini batch like forward is finished, you're updating your parameters. So it could also be done in parallelization, and it also makes you search through a large parameter space. So these were the three mini batch gradient descents, and here are some visualizations of basic regular gradient descent. This is just like a convex quadratic function, and you can see that it steps towards the minimum point gradually as you move on. And however, for like these kind of systems, so the darker means the function values are more smaller, and you in this kind of setting, like there's like a saddle point here, but it's possible for or like regular gradient descent algorithms to get stuck in saddle points because the gradient's zero, so or maybe be stuck in a local minima. And also, oscillation is one problem in gradient descent, because right here, you actually want to go to like this direction towards the global minima. But actually, because this direction of the gradient is too large, it's kind of hindering. What do you mean by the 100% button in view options? Um, do you think it's too Shentong, do you?
Oh, I'm just answering the student. So I just I mean
Oh,
he
okay,
or
okay,
she
okay,
could
okay.
select the yeah
Oh, okay, okay, okay. Yeah,
the
yeah, yeah. Oh, I thought
100%
you were talking to me.
view
Okay, okay.
options.
Yeah, yeah. Sorry, I misunderstood. Yeah, so in this kind of case, oscillation is like a problem, and it's kind of hinders you from actually going straight towards the minimum. So we want to make some modifications, or in gradient descent such that we can prevent these kind of behaviors, such that we can reach to convergence to a global minima as fast as and accurate as possible. So the first method for fixing gradient is Newton's method. So this intuition comes from uh, actually, so gradient descent, you can consider this as a form of, so from the loss surface, you are actually locally trying to find the first order approximation, which is the gradient of the loss surface. And you're actually finding the direction of the largest decrease. And that's why it's just a simple gradient. But in Newton's method, the idea is why not do a second order approximation also added to the first order approximation. So if you see here, Newton's method actually uses a second, the Hessian to actually to actually consider the second order approximation, and it tries to take the direction of the step to maximize the decrease. So it actually scales the gradient with the Hessian and enables using a larger learning rate. And it works well in convex settings, and it kind of makes you circumvent in like some obstacles throughout and like go to straight to the minimum points. And so if you see here in the figure, you can see that the regular gradient descent in this like convex setting kind of, while it's like oscillating, the using Newton's method, it actually gets you straight to the point. However, calculating the Hessian is actually somewhat computationally intensive because you have to always compute the second order derivative. Although for the gradient, we use like back propagation to do it. And also, if you see here, Newton's method gets more attracted to saddle points because it's using the Hessian, like the second order approximation. So if you see here, it's the same setting where there's a saddle point in the middle, and like these top and the bottom are like minimum points. And if you can see that the uh, re regular gradient descent kind of perform well, but the Newton's method actually gets stuck and gets more attracted to the saddle point. Yeah, so the next method is Armis prop. So this one kind of considers the square of the gradient and tries to keep an accumulation of the square of the gradient, like a weighted accumulation. So you can think this as if you, so for each network parameter, if you've like already accumulated much gradient, you're going to divide the gradient step by the square root of vt plus 1, which is like the accumulated weighted sum. So basically, if you have already went through that direction a lot, then you'll be actually taking a smaller step. So this kind of is essentially like adapting the learning rate according to previously accumulated gradient values for each parameter. And it kind of prevents you the oscillations by having smaller and smaller gradients. And also it expand. So it also makes you have take a larger step depending on the parameter. So if like a parameter, if there's a parameter that's like not really frequently tuned, then if it's like tuned for the first time, the VT plus 1 is going to be small because the gradient has been small and you haven't changed this parameter like yet. So basically it's going to make you take a larger step for like unseen or untuned parameters. So that's kind of the spirit of Armis prop. Excuse me. And basically, if you see here, regular, in this case, regular gradient descent kind of oscillated out here, but by Armis prop, by keeping the weighted average of the square of the gradient, it actually lets you gradually move to the minimum point. However, in this kind of setting, when you have to move, you have to move to the same direction for multiple steps, like it's just a flat surface, then Armis prop kind of has a characteristic that it kind of ends up slowing you down too fast, because if you're moving like in the same direction, the weight will be larger and larger, and it's going to take smaller steps like every time. Yeah. Excuse me, can I get some? I'll get some water and come back real fast. Yes. Sorry, my voice was like going off. So yeah, so Armis prop kind of has that downside of slowing down too early when trying to go through a plane surface. The next, I guess, the most important modification that you make, which you're also implementing for homework 1 part 1, is actually momentum. So what this is doing is it's keeping, so it accelerates where the gradient is in the same direction, and it dampens where the gradient is kind of oscillating in different directions. So if the gradient goes like plus and minus, and it's oscillating, that means like you have to decrease your step size in that direction. But if you're like going through the same direction continuously, then that's kind of a sign that you can move with a larger step size.
Sorry to interrupt again. Do you think
Yeah.
you can zoom in a little bit more? I can't really read the formula.
Okay. Yep.
Thank you.
Uh-huh. Yeah, so I think this one is in appendix like 3.5.3 or something in your homework 1 part 1. But yeah, so basically what momentum is doing is it's keeping a weighted average of your gradient, and it's actually using that momentum value to update your parameters. So so basically like it keeps like the general trend by keeping a weighted average, and um, and it and and it really helps. It seems to really empirically be very successful and speeds up the convergence a lot. And I'd say I've seen people talk where if you want to like keep like one technique, it would be momentum. So and some people think that momentum is always a good thing to include. So I think empirically, I think it really helps also in non-convex situations in deep learning. Yeah, but there's one characteristic of momentum, is that it's actually a little bit reactive in nature. So here in this plot, you can see that regular gradient descent kind of just goes through here, but momentum, it kind of tries to fix the oscillating part by decreasing the step size of the oscillating part. But the reason it has to be reactive in nature is because it doesn't know until you change like the gradient direction that it's oscillated. So you have to like oscillate first to actually decrease the step size and make a modification. So that's why momentum usually is like reactive in nature, and to kind of do a more clever way to be like look a step forward. That's what Nesterov's accelerated gradient does. So what this actually,
I guess Manisha,
I'm sorry.
sorry, I
Yeah,
guess
yeah,
there's
yeah.
someone raising her hand. Yeah.
Yeah. So, in what situation can we use RMS prop and momentum? Like, what kind of data do we need so they work well?
So I'd say this is more of like the optimization side. Um, I think generally momentum is works well for like most kinds of data. I'm not really sure at this point. I've never heard like a specific data that works well with like RMS prop. To be honest, um, Shentong, do you know any like data that works particularly well with RMS prop? Um,
I guess it depends on the task, right? So if you have some data with, I mean, if you do something model on the audio data or something data, you can maybe use IMS prop or momentum. But
mm,
if you do some vision data, maybe you need to use SGD
yeah,
or
yeah, yeah,
add
yeah,
other.
yeah,
Yeah,
yeah.
it always depends on the task. Yeah.
Yeah, yeah. It kind of depends on the task, but yeah, also I kind of generally like many of the things are like kind of empirical. So empirically I think I kind of remember that a computer vision task you usually use SGD, and and yeah, so I know that's like not kind of a perfect answer to your question, but usually if you have a data and like a task, usually you can find like empirically which optimization algorithm works best. But momentum, I know that it kind of works well for like general cases, like for like most of like data. So momentum is always good to have. Yeah, hope that answered your question. So we were moving on to Nesterov's accelerated gradient. So what Nesterov accelerated gradient does is it takes a step towards the accumulated gradient first. So if you see here, it's actually taking a step, but it doesn't like update the values. It just takes the steps and then calculates the gradient as if it were to take that step, and it uses that gradient to the accumulation of the momentum, and then it uses that to update your parameters. So it's somehow like incorporating some future information into its current step. So it kind of prevents from being like, for momentum being reactive in nature. This is kind of incorporating the future information of the inside this current step by trying to take like a step ahead and computing the gradient from it. So there's actually a few versions of Nesterov's accelerated gradient, and I think there's like two versions plotted here, and you can see that uh, momentum is like kind of slow here, but by looking at like future, you generally know that you have to go to like this direction. So um, Nesterov's accelerated gradient kind of converges faster and steps away to the minimum direction faster. Yeah, so finally we're here to Atom. Atom is like usually the most well-known and mostly used, commonly used optimizer. Like if you have no idea like which optimizer you use, you usually go with Atom. Last semester most of the TAs recommended to just use Atom for most of the part twos. Yes. Um so basically what Adam is trying to do is it's incorporating what we saw in RMS prop of the weighted average of the square gradients right here. And so this kind of enables to update each parameter in like a different modified learning rate, because we're like dividing this like square root over here. It's like really similar to RMS prop, but it's also including this like momentum um, of like it keeps track of the average weight of the gradients. So it's doing both. And actually, this v hat and m hat exists to it's a way to uh, have an unbiased version of vt and mt. So that's what Adam is doing, and then you update the parameters according to it. So Atom Optimizer is like very known for its convergence, and usually like if you have no idea, or if particularly if you don't have like if you don't know like which optimizer would fit with this kind of data, you generally just go with Atom Optimizer would definitely be your first choice. Yeah. So um so this is kind of a comparison of like atom and momentum and armis prop. So you can see that gradient descent kind of just oscillated out here. Atom tries to converge it as it goes. Armis prop kind of like when it goes to the same direction, it kind of it's actually decreasing the step size too fast. And for momentum update, it went like past and then it came back because it's like reactive in nature. Yes. So another interesting thing is actually there are some like heuristics, but usually they're mostly empirical, depending on which task and which data you have. And one interesting thing is sometimes like using SGD and momentum results you in a better minima. But in terms of convergence and like how fast you can reach near the minima, usually uh like adapting learning rate and like Atom uh like optimization methods such as Atom usually works better. But there are some reported cases where SGD and momentum is better. And as like Shantong mentioned, computer vision tasks, usually people just use stochastic gradient descent. Yeah. So the next part of is like initialization of neural networks. So so initialization is like important because first of all, like what would be the best like initialization point? Like it would be like perfect if you like start at the global minimum, but you can't do that. That's why you like need all of these like optimization algorithms to like reach to the minima. And so uh actually depending on like how you initialize your network parameters, it actually could resolve prevent your gradients from exploding or vanishing. And it de- it kind of makes you like, depending on where you start, um it kind of makes you how fast you can converge and how which minima you can like reach. So initialization of the network parameters are is a really important factor. And I want you guys to think like why what happens if you initialize like a network with like just with constant values, like all the same values, or like maybe like zero. Try to think like what happens during training and what happens if you just like set everything to zero and start. Yeah. So I think I didn't give you like enough time to think about it, but if you think about how the network parameters are. Oh yeah, yeah, yeah. Shall you're totally right. So it learns all parameters in the same way. So basically, so if you start with all constant values and all the same values, all the weights are going to move in the same direction, and you wouldn't end up learning anything. So there are many choices on what kind of like distribution you'll use for initializing like Gaussian or uniform, and I'm trying to introduce like two really successful initialization methods, which is K-mean and Savior. And for the PyTorch, if you look through the PyTorch like document, you can find that the default initialization when you like define a model, like an MLP, if you define it, the default initialization of network parameters is K-mean. So that kind of shows you that K-mean is working pretty well. So for K-mean initialization, it actually tries to initialize the network parameters with a Gaussian of a zero mean over here. And it actually tries to have a variance of square root 2 over ni, where ni is like the number of nodes in layer I. So this is what K-mean did. And you can read through like some notes I wrote in here, uh, I mean the notes written in here, and also I kind of linked to the original paper, Sevier's paper, and Kaming's paper in the bottom. I think here, yeah. So I think this is Kaming's paper, but you can read through it if you really want to know how why this helps. Yeah. So basically this is showing like the vanishing gradient and like vanishing activations. So I think you might I think Biksha might have handled this in class, but as you go further inside the layers, um, you can see for here, like for a standard initialization, the values, um, for example, for layer 5, it reaches like almost to 0. So you can see that it's like vanishing. The values are vanishing, and it's like getting really small. And it's that the same thing happens for gradients. Like gradient vanishing is always a big problem. And because we're going backwards. If you start from layer 5, and if at the moment you're reaching layer 1, your gradient's like all near 0, so you won't be making much of an update of your network parameters. But instead, if you use like Savier's initialization, which is also um, trying to initialize as a Gaussian distribution of for your network parameters, you can see that it's resolving the vanishing gradients and vanishing activation value problem, and you can see that each layer has mostly the same value distribution for the gradients and the activation values. So you can see that from here that initialization can actually affect your convergence, because the values that it can have um, could could end up to some like weird distribution, like center really spiking in 0. So yeah, that was pretty much K-mean and Savier's initialization. And for K-mean initialization, I think you might uh, be reading K-mean's paper in one of the future quizzes. So it's just good to know that that K-mean initialization is a thing, and like it actually affects your training. Yeah, so that's all for me, and I think Shentong is gonna talk about more on optimizing neural networks. So yeah, Shantong, you want to go ahead and share your screen?
Yeah, let me share my screen. Can you see my screen?
Yeah.
Okay. So I will go for the recitation 3 part 2. And today I will talk about the learning rate scheduling, regularization, common pitfalls, and some tips for homework 1 part 2. So um, so firstly, I will talk about the your learning rate. So about the learning rate, so personal speaking, our learning rate is one of the most important hyperparameters that affects your model training performance. So I think if you were finishing the homework 1 part 2, you will know that the learning rate is very tricky to adjust and to get the performance on your Kaggle. Yeah, leaderboard. So I think it is usually helpful to annual the learning rate over time. And some trick is that tricky part is that you can decay the slowly and you'll be wasting some computation bouncing around the with some little improvement for a long time. But but if you decay it too aggressively and the model will I mean will decrease very quickly and it will not be able to reach the best position. I mean the minimum that you can arrive. So for the I mean for the in this picture you can see on the on the on the left it's you can use a small learning rate. So if you use a small learning rate you will require many updates before reaching the minimum point. But if you have too high learning rate you will get rid of I mean the divergent behaviors among the minimum point. So you need to choose the optimal learning rate and that so such that you can reach the minimum point. So the learning rate is very tricky and you need to very careful to select your learning rate. And but there are some three common used methods to I mean if your learning rate is too low or too high, so how can we avoid that, or how uh, can we do to reduce the learning rate or to the first way is to reduce the learning rate by a factor every few epochs. Something like if your typical values might be reducing the learning rate uh, by zero point 0.5 every 10 epochs or every 20 epochs, or you buy zero point 0.1 every 20 epochs. Yeah, I mean, this X or Y is very dependent on the type of your problem or your task or your model. Yeah. And the second way is the reduce plateau. So, I mean, this method is like to watch your validation error performance while training with a fixed learning rate and reduce the learning rate by a constant like zero point 0.5 or zero point 0.1 whenever the validation array stops improving. So sounds like in this figure, if your I mean your learning, if your validation loss is not decreasing, you may need to decrease your learning rate because yeah, you can use PyTorch or some TensorFlow tool to see your validation loss. If it is not decreasing, you need to, I mean, you need to decrease your learning rate. Yeah, and the last way is to reduce the learning rate according to the following. I mean, the mathematical form is like exponential decay. So it's also a way to, um, I mean, the step decay is preferable because the high parameters it evolves are more interpretable than the hyperparameters k in this form. So they're exponential decay, or you can like, yeah, it's very simple to say, right? So alpha, I mean the alpha equals to alpha 0 times e powers minus k kt, and the 1 over t decay is like you can reduce the learning rate according to this formulation. Alpha equals to alpha subscript 0 alpha o over 1 plus kt. So here is the t is represents the epoch number. So I mean, if the number is decreased, you can see the alpha uh, sorry, so t is increasing and your alpha will be decreasing. So your learning rate will be decreasing. These are some ways that you can use uh, in your practice. So the next part is about the regularization. Mm, I mean, the overfitting part is very important. Is also very important because in many cases you will overfit it to your training data, but yeah, but you can do well in the test data, so you will not have a good generation performance. Uh, overfitting is a modeling error array that I mean that that occurs when a function is too closely fit to a limited set of data points. So in this figure, in on the right on the left figure, is you can see if the if the dot point is a training data, but the the circle points are training data, and the dotted lines are that is your model. So you can see the training data is quadratic, but your model is linear, so it's not it is unfitted. But in the middle fig, your model is is a good fit or robust to your training data. And this for the right figure, it is very overfitted to your training data because your model fitted each training data point. So if you have a new data point, it will not, it will not get good performance on your new data. So in the in this, in this curve figure, you can see the training and the test set. And if your model complexity is very high, and you can get a good performance on your training data, but your test data performance is not guaranteed to get a good performance. It is not guaranteed to uh, improve. So you may need to, if you got overfitting, you may need to decrease your model complexity a little bit. But yeah, it is also very tricky. If you maybe you're not maybe your model complexity is not very high, so your test data set performance is not good enough. So you may need to uh, increase your model complexity first, and you can see your test data set performance is decreasing. So at that time, you may need to decrease your model complexity. But yeah, it very depends. So for regularization in your neural network, there firstly we can use L1 or L2, and for it involves adding an extra element to the loss function, which will publish our model for being too complex, or in simple words, for using too high values in the weight matrix. Actually, in your implementation, it is very used to add the regularization in your neural network. You can just use the weight decay in the optimizer. Uh, for example, in your PyTorch, you can add the weight decay parameters in the SGD optimizer, and you will add this I mean, this regularization term in your model parameters. So for example, if the lambda is equal to 0.001, and you can see your, I mean, it is it will overfit your, I mean, your training point, training data point. But if the number increase, uh, sorry, there's someone talking. Uh, yeah, if the lambda increase, you can see you will not overfit to your uh, training point. It will maybe it will I mean it will generalize well to new data point, but for the right figure, for the left figure, it will overfit to the training points, so it will not get good performance to new data. So let me draw something. This is the L2 regularization, and this is L1. And L2 is plus all total, the sum of the, I mean the parameter square, and this is L1. You uh, you add the sum of the I mean absolute value of the parameters. Yeah, this is the regularization part. And another method for regularization is the dropout. So dropout is for each training batch, you can turn off some neurons with a probability. So I mean that this dropout motivation is very I mean it sounds like you mean in it sounds like you uh, avoid to overfitting, right? Because if we have uh, a larger model complexity, you will overfit to the test data. But if you have the dropouts and you can regularize a fixed size the model, actually you can average the predictions of all possible settings of the parameters. And yeah, and for the implementation, it is very you need to take care, because for training time, you may need to mask some neural outputs as zero with probability p. But in the test time, maybe some because you have mask some neurons outputs in the training time, but in the test time, you don't need to mask the parameters as test time, because yeah, so you need to multiply the dropout probability p to approximate the expected output. So I guess the dropout I is in your homework one part one, but yeah, you must be careful in the training time and testing time. So for a typical dropout rate, you may choose 0.1 to 0.5. Yeah, it's also a high parameters. Yeah, you need to choose, you need to adjust the, I mean the dropout rate. I guess it should be in the homework 3 part 2 or homework 4 part 2. You may need a lot user dropout to avoid the overfitting, and you can add a regularization in your neural network. Yeah, I guess, yeah, as I said before, it addresses two problems. The first is overfitting, and the second is generalization. It will, I mean, the model combination always improve the performance of machine learning method. So in the right figure, you can see that with dropout, we can decrease the I mean decrease the classification yeah, error a lot. So yeah, you can get a good performance. So another regularization method is a batch norm. I guess a batch norm is also in your homework run part one. So batch norm is also, I mean, the motivation for batch norm is the non-stationarity of unit activity during the training. that will require you to adapt a stationary input distribution. So I guess the professor will talk about more about the batch norm. And as you see in the batch norm paper, it says it can solve the problem, the internal covariate shift. So yeah, and so I guess you have done have been doing the homework on part of two. So you will see you will feed a batch data into your model. So in the batch data there will be some internal covariate shift. So you may need to use a batch norm to improve your model performance. But more details the professor will talk about in the lecture. Yeah. So uh, this is the formula for the batch norm. Mm, yeah. So the batch norm will make you have a good higher learning rate, and yeah, it also very with batch norm normalization, back propagation through a layer will be very stable, and it will get a faster convergence, and it will also regularize the model. Yeah. So, and there will be other regularization methods in neural network, like early stopping, gradient clipping, and parameter initialization. Yeah, as Alex said before, you can use k-mean initialization or other methods. Yeah, they were not regularization in neural networks. Next, I will talk more about the common pitfalls. I mean, the first, I guess it should be zero initialization. This is would be a very bad performance issue because if you initialize your neuron with zero for each neuron, yeah, each neuron would be identical, so it will not be uh very good to your very beneficial to your performance. So another is you will forget to shuffle the data set. So in your homework part two, you may need to shuffle your training data as you are training your model. So yeah, and the third is the choice of your learning rate. As I said before, if you choose a very large learning rate, you will not converge your model. And if you will choose a small learning rate, you will get rid of the local minimum. And also the choice of the batch size is very important to your training. And I guess uh, in my practice, I the choice of the batch size is very important to feed your GPU memory. And yeah, I guess if your GPU is very powerful, like 3090 or something else, yeah, it can feed a larger batch size. But yeah, but it's not guaranteed a larger batch size needs to better performance. But for SGD optimizer, a smaller batch size can lead to better performance. So yeah, you may need it also a hyperparameter you need to choose. And yeah, so there are also some problem with momentum method. Yeah, it might be prone to local minimum. So yeah, actually in your model you may want to find the global minimum, but yeah, it's very hard to find the global minimum. But yeah, it so there may be some problem with momentum, but yeah, you may need to have a try using SGD with momentum or Atom with momentum. Oh yeah, there are also other common pitfalls like batch norm. So yeah, in the batch norm paper, it says uh, the it says they they should use like a batch norm, renew or relu batch norm. I mean, the order of the batch norm and activation functions uh, actually the matters. So you need to careful about this one. And also some tricky things using batch norm and dropout. So in the I mean in the dropouts in this paper it says that they work against each other, but actually in the practice you may use these two things together for uh, I mean for vision data or for audio data. Maybe you can have a try in your task. And and the third thing, next thing is you may forget to normalize your input data. Like if you train, I mean, if you have a training on the image data, net data, you may need to get the image image mean and the standard deviation. If you train your model on the CFAR 10 or CFAR 100, yeah, the mean and the standard deviation will be different. So you may need to careful about this. But if you are using batch norm, this would not be a problem. Yeah, and for in the batch loop, you may need to use a AR scheduler to stable your training process, and and the most important thing is that you need to do the optimizer zero gradient to your, I mean to your gradient of all your parameters in your model. If you don't do this, yeah, I mean, you will not get a good performance in your model. Yeah. And there are also some tips to improve your models, like assemble and drop out and deeper or wider. Yeah, maybe you have read some ResNet, DenseNet, or some other more advanced models in this class later. And and also you can use a learning rate scheduler like cosine annealing learning rate scheduler or other. Yeah, and the other thing is that you can also use a random initialization. You will have a problem. Maybe you need to use a warm up to your learning rate, and you can get a stable learning process. So yeah, and I think that's all for this recitation part two. But I also go through some code for this part, but it will be very quickly. It will be very quick. Uh, there's some questions in the chat, right? Yeah,
Yeah, so
Alex has
I think
answered those.
yeah, I think people kind of asked about like the orders and like where to have like a dropout, and like is it okay to have like a batch norm layer and a dropout layer together, and like the order of those. Do you have like any recommendations?
Oh yeah, as I said before, in this paper, I mean in the dropout paper, it says that the dropout is against the batch norm, but I think it very depend. From my side, I think we can try both in your task, but if you uh in, I mean in this class, in the homework 3 part 2 or homework 4 part 2, you may use dropout, but
Mm-hmm.
for some vision data, you may need to use batch norm and drop out both. But yeah, you can have a try, I guess. If you want to know more about this one, you can read this dropout paper. And also for the order of the batch norm and the activation there, like ReLU, I guess it should be for the reference paper. It say it will be linear ReLU and batch norm. Yeah, I guess this order should be uh, this the second order for the, I mean for the is correct in the reference paper, but also someone use uh the first order. Yeah. Yeah, I guess you should use the I mean you should use the second order in the reference paper. You can see the batch num paper in this link. Okay, and next I will share my yeah, this I mean this code is about the add the paper I mean not the paper, but add the learning rate scheduler or some tricky regularization in your neural network, and you can see the performance or the training loss or validation loss will be very very I mean it will you will get a very stable learning process. Yeah, so I will go through this code very quickly. So for this part, it's just import all the models that you will need in this code. Yeah, it's very easy for you guys, I guess. And for this part is for the, I mean, yeah, it's just get the minutes the data set from the torch vision data set. And this is a training data loader and validation data loader, test data loader. And yeah, this is the training size, validation size, test size, and you can plot some samples from this training data set. Yeah, you can see this. Yeah, this is a minutes data set, and this is a function for training. I mean, one epoch. Yeah, it's very. I mean, this is a for loop for enumerate your training data loader, and you will get the inputs and the labels. And yeah, there is a parameter gradients, and this is a forward. This is a loss, and you will get the loss, and you will dot backward to get to calculate the gradient of each parameter in your model, and you will use the optimizer dot step to to update your parameters. I think this is very easy for you guys because you have implemented in your homework one part one. Yeah. So yeah, this is for training part, and this is a training step. Yeah, this is like yeah, you got you define the epochs for you calculate all the epoch all the training process. This is the evaluation. I mean the most important part is you need to with torch.noGrade for your evaluation code, because if you don't have this, you will have you will also, because if you go, I mean the forward backward, you will calculate the gradient of your parameters in your model during the evaluation stage, but you can't do that. Yeah, so this is a visualization for some loss. Yeah, it just plots the training loss and the validation loss. So this is my toy model. Yeah, this is linear renew and linear renew and linear. So yeah, this is SGD optimizer, and this is training infer, and this is I guess it's yeah 100 epochs. You will see if I add, this is a baseline code because I didn't add any tricky methods, as I said before, like learning rate decay or cosine scheduler. You can see that the learning process is very unstable. You can see very I mean, yeah, you can see the loss is not decreasing stably, so it will this is not what it is not what we want that. So let's add a scheduler in this training part. We add a scheduler, and then we train that. You can see that the curve of the the curve of the training loss and the validation loss will become a very very stable, right? So yeah, this is a dropout. You can have a try because I will upload this code to the website, and you can have a try. If we add the dropout, what we will get this about, yeah, we will get about the training loss and validation loss. And this is a batch norm. And after adding the batch norm, you can see that the training loss is very good, right? So you can see the training loss is very stable, but your validation loss is not, it's not good. It will, it is very not, it is not very stable. So for, so for batch norm, I guess you may be careful to use that, but yeah, but I guess for batch norm and dropout, you may need to careful to use that for your training model, because if your batch norm is not it's not good in your task, you maybe choose another regularization method. Yeah, so during your training process, you need to plot the training loss and the validation loss with the epochs or with the iterations in your in your model. Yeah, I guess mm, yeah, I guess this is for the following code is very similar to this one, so maybe you need to go through this. Uh, it is very easy to see what's going on here. Yeah. So I guess that's all for today. Does anyone has questions?
Yeah, sorry, I have a question.
Oh, yeah.
Please go ahead.
Okay.
Thank you. So I have a question in terms of the evaluation. So you declare the model, the EVAL. So do we still need to declare that with no grade, this function? So, can we, do we need to use them both, or just use with no grade, or just use evaluate?
Okay. Are you talking about the the function? This function?
Yes.
Yeah. Did you mean this one? Like model.eval? Yeah. You need to define this. Yeah, sorry, I forgot this, but yeah, you need to define this one to change your model from the training mode to the evaluation mode. And I guess if you change this one, you will also need to use this one. Yeah, I guess it's my from my side, I always add using these two terms together, but you can have a try if you just use one of them. But I
I'm
promise
looking
you,
at
you
online
can.
and it says both are necessary. So no grad is for the auto differentiation engine, and the eval mode is to tell the layer, the batch normalization or dropout layer to be the eval mode.
Okay, thank you.
Yeah.
Yeah. Maybe you can just use one of them. Yeah.
No, you have to use both of them for.
Okay.
Well, I guess no grad is optional, but if you use it, it's faster to validate.
Yeah.
Yeah. And from my side, I always use two of them. It will get very faster evaluation. Yeah.
Thank you.
Okay, so I have a question about the scheduler. Can you scroll down
Oh,
to...
yep. Training part, right? Oh, yeah, here, right?
Yeah, so you said we can get a better performance after using the scheduler, but you didn't explain what is the scheduler. Okay, it's the learning rate scheduler.
Oh, yeah. I as I said in the point part, as I said before, the scheduler is like decaying your learning rate.
Okay.
So yeah. So it will. There's a lot of learning rate scheduler in the PyTorch, like cosine learning. those
Okay, I see.
other
Sorry, I
methods.
missed that.
Yeah. No problem. Does anyone has any question? Yeah, and in the chat, can you explain the optimizer zero grade again? Yeah, I mean the optimizer zero grade is for you just initialize all the gradients of your oral parameters in your model to 0, and if you don't do that in the Lex epoch, you will not get good unlike because you are accumulating your gradients is not good. Yeah, I will post this this code to the website.
Sorry, I have one more question.
Oh yeah.
So you mentioned that if we start all the parameters at 0, then we will learn nothing.
Yes.
But why is that? Because the gradient for each parameter is different, so we will updating them individually and separately. So we will end up getting a totally different number values, I believe.
Yeah, makes sense. I mean, it's not you can learn something, but I guess if you zero all the neurons zero in the first point, you will each neuron is the same, right? Because if you calculate the gradient to each neuron, it will be same. So the parameters will be the same, and you will not get a good performance. But you can have a try if you want to see if I guess it should be you will get the same neuron for each you will get the same gradient for each neuron. Does it answer your question?
Okay, I will try that, but I don't think we will end up getting the same weight for each parameter and for each neuron. But I will try that.
Yeah, okay, yeah. If you want to see, you can have a try. Yeah, what is n dot flatten? Oh, okay. This is like if you have a tensor of shape, like 2 by 2, and you will flatten, you will get 4, I guess. Yeah. It's like flatten your tensor to to a
1D.
loose shape. Yeah.
Okay. If there's no more questions, I think this is it for today. Thanks everyone for coming.
Yep.
Yep.
Thanks, Sarah.
Thank you.
Oh yeah.
Yeah, I'll just end the meeting right now.